Hi, today we're solving problem 41. In this problem we're given the definition of a pandigital number, which makes use of all of the digits, 1, 2, the number of digits in the number, exactly once. And we're given the example of 2143, which is a 4-digit pandigital, and is also prime. We need to find the largest n-digit pandigital prime that exists. Now there are two ways to solve this problem. The first way is calculate all of the prime numbers and filter the ones that are pandigital. And we can also do the reverse. Find all of the pandigital numbers and calculate the ones that are prime. So when calculating all of the ones that are prime first, we would use the sieve of Eratosthenes, which gives us all of the prime numbers up to a given limit. We would use the limit to be the largest possible pandigital number, which is 9876 all the way to 1. We could run that and we would get our answer. But it's pretty slow. We could make a few optimizations with that problem. One that we can do is reduce our upper bound. When we look at our 9-digit pandigitals, we see that none of them are prime. And when we dig a little deeper, we understand why that happens. Because when you have a 9-digit pandigital number, no matter what the rearrangement, you still have the same digits, and the sum of the digits is always the same. With a 1 to 9 pandigital, you have a sum of 45. And we know that a number is divisible by 3 if the sum of its digits are divisible by 3. So with that, we know that we can never have a 9-digit pandigital which is prime. We can apply the same rule to 8. With 8, the sum is 36. And we know there that we, again, cannot have an 8-digit pandigital that is also prime. But with 7, we might have one. So we set our upper bound now to the largest 7-digit pandigital. And so we can run that, but it's still pretty slow. So let's try the other way, where we first generate all of the pandigital numbers and then calculate which of those are prime. Now, when we're generating our pandigital numbers, we can find all of the pandigital numbers given a number of digits, and we can actually filter down on the number of digits using the same divisibility by 3 rule. We actually find that only 1, 4, and 7 are the possible number of lengths of the pandigital numbers that may also be prime. And so that reduces the search space greatly, and we find that to be the faster answer. So let's go ahead and implement it. I'm going to switch over to IntelliJ. So I've already copied into the util object the isPrime method that we'll use in the second step of our search. But the first step is calculating all of the pandigital numbers. First, we need to calculate what are the possible number of digits in these pandigital numbers, so we create a val digits. We first start with the range 1 to 9, and we're going to filter on these to see the ones such that we won't get a multiple of 3. So we're going to filter not. Given the number of digits in a pandigital, we can calculate the sum of all the digits, because that's just going to be the sum of all the numbers from 1 to n. To do that, we can do some simple math. We just do n times n plus 1 divided by 2. And if this is divisible by 3, then we don't want it, so we remove it out. And if we println digits, we see that we only get 1, 4, and 7, which is what we expected. Now the next step is, given digits, calculating all of the pandigitals with digits. Now, first we're going to calculate just the range of 1, 2 digits, and each of these elements represents one of the digits that will be in our final pandigitals. And we need to rearrange these to calculate all of the different ones, so we use the Scala permutations method, which gives us an iterator of all of the different rearrangements. Then we take each of these rearrangements, which is an index sequence of integer, and each of these integers in this index sequence represents one of the digits, and these are in order of how it should be in the number. And now to take this index sequence of the digits and collapse that into a integer, what we can do is we can take that index sequence, convert it to a string with no spaces or anything, just directly with mkstring. And we need to convert this to a numeric type, so we're going to use a long, because our utility is prime wants a long. So we're going to do that, and we're going to convert this to a list so that we don't have an iterator from permutations. Now that we have pandigitals, let's calculate all of the pandigitals, which is just taking each of the digits and calculating the pandigitals for that. And we don't care about having the nesting for each of the digits, so we're just going to collapse all of those. So we're going to use a flat map on digits. So we're going to do digits, so flat map, which does a map on this and then a flatten. And for each of these, we're just going to use the pandigitals method here, passed as a function. So then what it's going to do is it's going to go over each of the digits, 1, 4, 7, generate the pandigitals, and at the end, we have an index sequence of longs, which is all of the pandigitals to go through. Now we just println our answer, which is going to be all pandigitals, and actually maybe we can just run this first to see our pandigitals. So we see all of these different generated pandigitals. So first we have the 1-digit pandigital, then the 4-digit pandigitals, and lastly the 7-digit pandigitals. Now we need to get the prime ones, so first we can filter the ones that are prime. Now we can run this again and we get the prime pandigitals. And all we need now is the greatest of these, so we do dot max, and this gives us the maximum prime pandigital. And we get our answer. So that's it for problem 41. I'll see you next time when we solve problem 42.